that is the picture of the derivative of f at 0 acting on the box. The derivative preserves vertical and horizontal, it stretches horizontal and it contracts vertical. And so my picture here amounts to saying that as long as you're close enough to the origin, the difference between the actual f and the action of the derivative is second order and is not going to make too much difference. So we will see a picture that looks like that. So that is the main idea. And then once you have this picture, you can sort of do it again. You can say, let's look at, you can just keep iterating. And you're going to find that the box tends to collapse vertically and keep stretching out further horizontally. So I can look at this piece and apply essentially the same argument to it. And it will stretch the image of that, or stretch across, and it will shrink in the vertical direction.
You've taken RU as the horizontal.
Yes.
So it should contract along RU.
You step, no,
DF inverse contract.
the inverse contracts RU, so F expands RU. So the idea in this picture is that the horizontal is getting stretched, vertical is getting contracted. And so if I just kept iterating the derivative at the origin, I would see everything would be linear. You can see how you contract vertically and expand horizontally. And the idea is that the non-linear map copies this behaviour well enough that as we keep doing it, we're going to always get so you want to make some kind of inductive argument that says that after you've iterated n times, you have a sort of strip that stretches all the way across B in the horizontal direction, and that the vertical thickness of the strip is shrinking exponentially. So, so you make it some sort of inductive argument. That sort of, or the D if to the N of B intersect B contains also a strip and has a width less than or equal to lambda to the n times delta in the vertical direction. For some lambda, which is less than 1. Of course, it's positive lambda. And the number lambda is essentially the number that controls the hyperbolicity. You can't use exactly the number you have here, but any number that is just slightly closer to 1 will do. So if, so you get a picture like this. And then if you take the intersection, so But we could call this strip ECN. And really what you want to do, so really what you do, the proof of the inductive step is that you keep doing that. And at the next stage you look at EC again. So at each stage you look at SE and intersect. With an SE and that gives the next stroke. So you can keep iterating. So because of this sort of vertical collapse, you end up getting a graph. And that is going to be the graph of your unstable manifold. So the intersection from n equals 0, so S0 is just the whole box, and the intersection from n equals 0 to infinity of the SEN is the unstable manifold. Okay, so that's probably the simplest argument of this type. There is another way of thinking about what we did here, which is really where the name graph transform comes from. If I think of my box B, and I think about functions that might be the graph. So I guess I should say that the idea of the unstable manifold is that we have this fixed point at the origin. The idea of the unstable manifold is that it's invariant under the map and things get stretched outwards. So another way of thinking of the argument I just described is you could look at the box B, look at all maps, look at all graphs of maps, say sigma from BU delta to BS delta. These are all candidates to be the graph that gives the unstable manifold. And then if you apply the diffeomorphism, the graph of F composed with sigma stretches across B. So if I started off with sigma, the graph actually goes further, and then you just cut off the ends. So maybe so F hat maybe is the graph transform. F hat turns sigma to graph of sigma cut down to the graph of a function of BU.
What is sigma, is it?
So sigma is just some function from BU to BS. So we think it's all graphs that we could draw in the box, and then we, given any such graph, we can apply F to it. We essentially get another graph of the same kind, except that we get the stuff we just forget about the irrelevant stuff that sticks out. And so there are two nice things we can say. The first nice thing you can say is that the C0 distance from F hat sigma 1 to F hat sigma 2 is strictly less than some constant times the distance, the C0 distance from sigma 1 to sigma 2 for some lambda less than 1. And the reason for that is visible in the picture. I will look at vertical separation of the two things. When you apply the diffeomorphism, all those vertical things contract. So you get a contraction in the C0 topology. The other thing is that if if I think of Lipschitz, the graphs of Lipschitz functions, they're going to tend to stay Lipschitz. So if sigma is, say, L Lipschitz, so is F hat sigma. And why is that? Well, the Lipschitz property says that it says that the distance from sigma x to sigma x prime is less than or equal to the distance, is less than or equal to L times the distance from x to x prime. And now, if we apply F hat, F hat is going to tend to move, it contracts vertical things, which helps with Lipschitzness. It also spreads x and x prime further apart, which also helps with Lipschitzness. So in fact, your new graph is not only Lipschitz, it is going to have a better Lipschitz constant, but it is at least as Lipschitz as what you started from. So this operation, you can think of the graph transform as acting on the space of L Lipschitz maps, and it is a contraction in the C0 topology, and it preserves the Lipschitz property. So they're really the two key properties of the graph transform. And then you have the idea that, well, if you have a contraction, it's got a fixed point. So if hat is a contraction, and then you find a fixed point. So you can find a graph that is invariant under F hat, which is what we're looking for. And then once you've found your invariant graph, you can then proceed further. So suppose I've now found my, so if I have sigma equals sigma.
Excuse me.
Yeah.
I'm kind of lost. So we're trying to find an unstable
Manifold, yeah.
manifold.
And so the idea is the unstable manifold is going to be the graph of a function.
Okay.
And it's going to, the unstable manifold, actually I drew that picture, this picture's not drawn correctly because it should be tangent in the middle to the unstable direction. So the idea is that the unstable manifold that we're looking for the fixed point is going to have to be tangent to the unstable direction. And when we apply the diffeomorphism, everything in this graph is going to sort of move outwards and stay on the graph. And that means it's going to be a fixed point of this graph transform.
Graph of what?
So it's some, we have some sort of box here. This is my BU cross radius delta cross BS radius delta. And so sigma is just a graph from BU delta to BS delta. So graph looks, basically this piece of unstable manifold looks like a disk. And it's approximately horizontal, which means we can think of it as being a graph over BU, and the value of the function sigma just tells you the height that it's at over a given point in RU. And the function sigma is going to be moderately close to being identically zero. So we see something like that. And so the idea is if you start off with a Lipschitz, if I start off with Lipschitz functions and my f is nice and smooth, Lipschitz graphs are going to transform to Lipschitz graphs and they're going to get closer to each other in the C0 origin. So I'll be able to find a Lipschitz invariant graph. And then you can sort of take a point, now that we know that this graph is invariant, I can then start thinking about trying to show that the graph actually isn't just Lipschitz, that it's differentiable. And what you do is you, if I have some point, say x on it, there will be, if inverse of x will be another point on the graph. And then you can start looking at vector spaces. These will have to be of the, they'll have to be of the same, they'll have to be of dimension u, so that they're candidates to be the tangent space to the graph. And if you look at vector spaces at x of dimension u that are approximately horizontal, maybe more approximately horizontal than I drew those ones. But then if you apply df, these approximately horizontal spaces are going to, well, you can apply a graph transform to these spaces. They'll tend to become closer to each other in the stable direction and stretch out. And so you can sort of recycle the graph transform argument to find the tangent space to the unstable manifold. And so if I want to find the next stage of the approximation, I go to f to the minus 2 of x, start off with candidate spaces there, move them forward 2 steps. And so you can, this is the kind of argument that you can do. So far I looked at the simple case, the simplest case where you have a fixed point of a diffeomorphism of Re. If we have the Nosov situation, situation. And I want to find WU, a leaf through X, which is going to map to a leaf through, well, I want to find an unstable manifold for X. And so what I have to do is look at the, f to the minus 1 of X and around each point you want to sort of look at the stable direction and the unstable direction. And now you can do the same kind of argument, that if I start with a box around, say, f to the minus 3x, it will map forward to a box that stretches horizontally across the box at f to the minus 2x, and then you get a strip that stretches horizontally across, which stretches horizontally across. And the further back you go, the more contraction you get as you come forward. And you can do essentially the same argument. So you have this graph transform method, which will produce the leaves that you're looking for. And so there are quite a lot of details that I've left out of the sketch, but does that give you an idea of? So by fairly naive methods, you can find what you're looking for. And then to get sort of to show that what you get is better than Lipschitz, you sort of first find the object, then you can start looking for derivatives at points in it. And if you want higher order derivatives, what you do is, instead of just looking at f, you can then look at the derivative of f acting on the tangent bundle of t here. And if f is a Nosov, the derivative of f is also going to be a Nosov. So with enough iterations of the method, you can find not just you can find the derivatives of the invariant manifold. And so the unstable manifold is going to be as smooth as the diffeomorphism that you start with. So I think that's probably as much as I want to say about, I think everything from now on is sort of detailed. This is the general idea. And basically what's really behind the picture of the image of a box squashing vertically, stretching horizontally all the way across is what's behind it all. You just sort of iterate that idea. Okay, so that brings me to the second thing I want to talk about, which is the fact that the invariant subbundles that you get are not just continuous. You can say something quantitative about how continuous they are. And this is needed in the proof that we're going to do tomorrow. So I want to say something about where that comes from. So I think maybe I'll use the middle board. So I think this goes under the name of the Holder section, invariant section theorem. So I want to have a vector bundle. And then I want to have diffeomorphism at the base of my bundle. And I want to have a bundle map that covers F. So F acts linearly. No, it doesn't have to act linearly. It's just a map. It's just a map on these bundles. Although the applications that I'm interested in, F is linear on the fibers. But that's not going to be needed just yet. But I do want to know that if contracts fibers. So that means there's a lambda which is less than 1, such that the distance from, say, FV to FW, this will be the distance in EX is less than or equal to lambda times the distance, this should be E of F of X, the distance in E of X from V to W. And this should work for all V, all W, all X. So fibers get contracted. Mu is a Lipschitz constant for the inverse of the base map. That may not be, that's what may be the easiest way to define mu. But what this really means is that the distance from Fx to Fy is greater than or equal to mu times the distance from x to y for all x and y are not base. And now we want to assume that lambda times mu to the, I think I'll use alpha, mu to the alpha is less than 1. Maybe before I come to the conclusion, I should say that we've got this bundle, we've got contraction of the fibers. Let me just say the graph looks like that, and I want to know that the map DF is C alpha. So in most applications of this, big F is a lot smoother than you expect. Alpha often is a number between 0 and 1, and F might be C2, C infinity. But you do need to, if you try to apply this with a map that's just doesn't have, well, is not very continuous, you can't expect terribly good things out of it. But so we have this setup, and now the first thing is that there is an invariant section, sigma from B to F. So invariant section means the obvious thing. It means that f of sigma of x is sigma little f of x. So if you look at this section and apply big F, things just move around inside the section. And this comes from graph transform. So I'm not going to worry. So you can start off, if you take a ball, if you take a large, you've got this vector bundle. So if you take a large neighbourhood of the zero section of your vector bundle and then apply big F, the fact that the map, and I guess my base B is compact. So my if I take a large enough neighbourhood of the zero section, it will contract in the fibre direction under big F, and the image of the zero section will be somewhere, but the contraction will overcome the tendency of the zero section to move away from itself. So some enormous neighbourhood of the zero section will actually map inside of itself, and then you can apply the graph transform kind of ideas and show that there is an invariant section. And it's clearly unique, because if you take something that's off the invariant section and apply big F, the thing that's off the invariant section will move closer to it. So we have the unique invariant section. And the main conclusion is that sigma is alpha Hurley. That's the main point of the theorem, so that you don't just get a continuous invariant section, you get something with a certain level of smoothness. And sometimes the alpha that you get from this theorem is kind of the best alpha you can expect to get, with some caveats. One is that you want a strict inequality here. So any alpha that you pick, well, unless this is the limitation on what you can do. But if this inequality is the limitation, for any alpha that you can pick, you can always pick a slightly bigger alpha that still works. So if you think of less than or equal to 0 and pick that alpha won't work, but anything smaller will. And that, I don't think there are a number of cases that have been worked out where it's clear that typically what you get from this theorem is the best that you can hope to do in terms of smoothness of the invariant section. That there are sort of generic families of big Fs for which the invariant section is no smoother, no better than this theorem predicts. Of course, there are also exceptional examples that for some reason can come out much, much smoother than this predicts.
If it's linear of fibers, then the only invariant section will be disease.
I guess, yeah, I guess that's true. So I guess I didn't mean linear. We'll see what I do mean. What I have in mind has something to do with linear. So the example, the sort of sample application of the theorem is to,
Maybe you mean a Brasilian bundle?
it might be, well, let me describe the application that is sort of relevant. So suppose we have a diffeomorphism and we have Tn is, well, let's just say E1 plus E2. We have an invariant splitting. And let's suppose that we have some numbers alpha 1 less than or equal to beta 1 less than alpha 2 less than or equal to beta 2. And I know that if V is in EI, that the norm, if I know that the norm of VI, but that's in between alpha I, norm V, and beta I, norm V. So this is the setup for from the Anosov diffeomorphism. Although I haven't actually assumed that the only thing that's missing from the Anosov setup is that in the Anosov setup I know that beta 1 is less than 1 and alpha 2 is bigger than 1.
It's clear that the stable and unstable, they are actually subbundles of the tangent body.
Yes.
I mean, you get some subspaces.
Well, the assumption in the Anosov case is that there are subbundles.
Yeah, subcontinental.
Um,
Assumption is that.
If you are saying they're invariant, then they have to be continuous. Or if you are saying
So
continuous, then they have to be invariant.
yeah, so I think I actually assumed in the lecture this morning that they were subbundles, they are continuous, they are invariant. And you always assume that you have bundles. So the kind of property that you're assuming, it's really obvious, it's obviously invariant under scaling of vectors. I think it's more or less obvious that it extends to sums of vectors. So the main thing that the main part of the bundle assumption is that the subspace that you're looking at has constant dimension, and that's really so in the case of the geodesic flow, the constant dimension is with an n-dimensional manifold. The constant dimension is n-1, and then there's one dimension left for the flow. Yeah, so I have set up like that, and now the claim is that and we'll assume that F is CK, and I claim that EI is alpha tilde continuous if alpha is less than k minus 1. The reason for k minus 1 is that we will really be thinking about the action of the derivative of F, and you lose 1 degree of differentiability by going to the derivative. So we have alpha less than k minus 1, and the other condition you need is that beta 1 over alpha 1, no, alpha 2, alpha, no, I'm not going to use alpha. because I've already used it, I'm going to use the theta. So theta was alpha over in the other theorem. So we have alpha 1 to the theta, that's the 1. That's the condition. So that's the inequality. And so the idea is that you can prove this theorem as a special case of that one. You have to think of the right bundle and then apply them. So actually probably perhaps I shouldn't have said well, yeah, I probably didn't mean vector bundle, perhaps. So what you do in this problem is, what you kind of like to do is to sort of, in each tangent space, you would like to split it up as E1 plus EU. But if you sort of introduce coordinates that do that, something circular will be going on, because the coordinates will be as smooth as this splitting. And we're trying to find out how smooth the splitting is. So we introduce, think of smooth splitting, say E1 prop, maybe F1 plus F2, that approximates E1 plus E2.
Couldn't you look at the actual df from a Grassmannian one?
I think that's really what I'm doing.
That's not true.
What's
But
that?
then you get the uniqueness of E1, E2.
Well,
Uniqueness and the alpha whole.
well, what's the alpha? I want to know what alpha is. Or, well, it's now theta. Yeah, so I think of.
So that E is just a final one.
I guess E, yeah, well, okay, let's just have a fiber bundle.
They're not as linear. Not metric on fibers.
Yeah. Yeah, I guess that'll work. Contraction, yeah.
In the Grassmannian you have contraction.
Yes. So, yeah, so what I want to think about is, so what I'm really doing is thinking about the Grassmannian of dimension of subspaces. Yes. And so I can think of such a subspace as, and I'm really interested in ones that are moderately close to E1. So such a subspace is close to E1. It's the graph of a linear function L from F1 to F2 that is close to 0. Right, and then the linear map F acts on L, so if I have a subspace and I apply, so df, so if I have a subspace, so it's close to E1x, it is and then the map, the map of the base, of course, is just the diffeomorphism with a f. The map of big F, what takes L to, let's call this subspace S. It takes S to df. And so it does whatever it does to L. And yeah, this is not going to take the zero map to the zero map. So yeah, so it's not a linear action. But it is, there is something linear forcing it to happen now. Okay, so that's the setup. And then all you have to do is look at the estimate of this theorem and work out what the corresponding numbers are over here. And so the mu is the strongest contraction you can see for the base map. So if
Alpha 1.
mu is, so yeah, mu is the strongest contraction for the base map,
That's alpha 1.
and that is alpha 1. That's good, and that means by elimination that beta 1 over alpha 2 is going to be lambda. And that works because there are two effects going on. You take, so you've got your map L from this space to this space, and then I compose everything with F, and F tends to contract the image, and the contraction factor is the weakest contraction you get is beta 1. So that's why we see a beta 1 up here. And then there's another thing that's going on which is good for you, which is that F1 is probably getting expanded. And the more you expand, even if you don't do any contraction here, if you just stretch things out horizontally, that brings the subspaces closer together. And the alpha 2 is the weakest expansion of the base here. So that's where this estimate comes from. Okay, so
Sorry, why is that capital F contracting on all subspaces if it's close to E1?
well, because my fiber bundle is going to consist of I'm going to use only subspace. I'm only going to use a neighbourhood of my. In this situation, I already have the invariant section, and I'm going to choose a neighbourhood of it that I know contracts into itself. And then the only thing that I don't know.
So you don't use the full Grassmannian.
Right. Yeah. The full Grassmannian is not going to be a good idea. I want because there could be the stable subspace, which would be repelling. I use only so in this situation, I already know that I've got the invariant section. I know if I take a sort of tubular neighbourhood of it, it will shrink into itself, and and the only thing I don't know is the regularity, right? Appealing to this theorem to find the regularity form.
The action on the Grassmannian has a repelling and an attracting fixed point.
A
repelling and an attracting section.
Yeah, I guess so. This is the
This is the attracting
this is the
section.
attracting
section.
one.
Similarly,
is the repelling section.
So what do you mean by the Grassmannian? Because
I mean, if you look at the action of
Well-
DF on the full gross median,
but you mean
so then there's going to be a repelling and an attracting section.
right? What's the fibre of this grass median? Because these spaces may have different dimensions.
Yeah, so then you need to look at GK cross GM
Flat
minus K.
manifold, you need to have a
Yeah, flag manifold.
pair of
Right.
subspaces.
So the
So-
flag manifold, yeah.
Okay, well, if I build the right bundle, I can see that this. So
One of them is
there's an attracting section which is the unstable. I'm trying to avoid.
Yeah, flag manifold.
A pair of subspaces.
On
Yeah.
flags, there's going to be a unique invariant flags. It should be contracting on flags.
So yeah, somehow, I would have to go off and think to build the right object
Right.
to have it. So yeah, if life was simple, actually for the geodesic flow case, it would be nice because these guys do have the same dimension. So you would have the repellent, you would just have the repelling
Yes.
space and the attracting one. And in the case where these have different dimensions, there must be some little trick that you can do to reduce it to the case of equal dimensions. Okay, so now that we've established, sort of described this estimate, I want to go back to some of the history. So, in the history of trying to prove that the geodesic flow is ergodic, there were various successes. So there was constant negative curvature. That succeeded because things are exceptionally smooth. The smoothest you get is not what is predicted by this theorem.
Busemann functions.
Was that?
Busemann functions are also smooth.
Yeah, everything. And so that's just an atypical example. The other case where people think Pop's real triumph was to do the theorem for surfaces. So why did he succeed with surfaces? And why did he get stuck when he went one dimension higher? Well, the modern answer is this estimate. In the case of surfaces, the bundles E1 and E2 are one-dimensional. When you have a one-dimensional bundle, these numbers are the same because there's just one number, which is what happens to your one-dimensional bundle. So if I can rewrite this estimate, I think as, if you try to rewrite it, I have alpha 1 to the theta bigger than beta 1 over alpha 2. So I think I have, that should be okay. And, or maybe now, I want to convince myself that when alpha 1, if alpha 1 is equal, so if alpha 1 is equal to beta 1, if I just put theta equals 1, this cancels. And in the Nosov case, alpha 2 is bigger than 1. So this inequality is true. So it works. So that would hold. And then the problem is if you move to one dimension higher with the geodesic flow, these bundles become two-dimensional. And beta 1, it's alpha 1 and beta 1 can be different. And you can't just do that cancellation trick. And the best theta that works can come out to be less than 1. And I think several people in the audience have mentioned something about quarter-pinched curvature. Then, so what happens if we have quarter-pinched curvature? Well, then it turns out that that alpha 1, so we have alpha 1 less than beta 1 less than 1. And alpha 1 turns out to be greater than or equal to beta 1 squared in that case. And so then if I have my beta 1 over alpha 2, alpha 1 to the theta, and I take, to the theta, and I take so if I replace beta 1 by, so if I replace alpha 1, so if I put theta equals 1, and then replace alpha 1 by beta 1 squared, I end up with 1 over alpha 2 beta 1. Is that a good thing to do? And I think alpha, in the geodesic flow case, alpha 2 times beta 1 is actually equal to 1. So in the geodesic flow, case, the behaviour is, if the bundles are sort of symmetric, the contraction you see is the contraction and unstable mirror each other. So in the case of if you have a quarter-pinched curvature, then you end up getting, you also get C1, stable and unstable subbundles. So you can do sort of the cheap argument in that case as well. And I think this was pure and Schumann. So this came well after Hoff, who obviously did not do, well, I think the sort of estimates that you're doing here. If Hoff had been doing these kind of estimates, he might then have gotten into the sort of things that Nosov and Sinai did. So that, and then if you don't have any of these conditions, the expectation is that the stable and unstable subbundles will typically be no better than is predicted by this theorem. But it's not, and there are examples.
So you're saying theta equal to 1 in those cases.
Was that?
You're saying in those cases
Yeah.
theta equal to 1.
Or better. So in this case, so for surfaces, well, theta is, I'd say, greater than or equal to 1. And again here, greater than or equal to 1. Here, well, theta equals infinity. And obviously, if you have something like the complex hyperbolic manner geometry, here theta would again be infinity. So there are exceptional cases where things are much, much smoother than the general theory would predict.
Well, actually, there's a result of Penrose-Laburi, which says that if the stable and unstable foliations are C infinity,
Yes.
then the flow is the time change of a geodesic flow on
Right.
finite covers and so on.
Yeah.
On a locally symmetric space. So essentially,
Yeah.
that is the only case. Up to finite covers and time change. Smoke
If,
time change.
that's if the flow.
If the foliations are C infinity.
C infinity.
Yes.
C infinity.
Actually,
Right.
they don't even need C infinity. They use the theorem of Gromov, which gives a CK where K depends on the dimension.
Yes.
It's
So
a polynomial of the dimension.
yeah. So
Quadratic in
yeah.
dimensions.
So if the
So if
right.
it's
So
smooth
if
enough,
if smooth enough.
then it has to be a time change of
Yeah,
geodesic
but the
symmetry.
right, but the sort of expectation that the level of smoothness that appear. So there are so let me make a little summary of that.
We use the
so-
theorem of Gromov for that.
Yeah. So Benoit, does he have an accent?
No, Fullo Labourie.
Yeah. So C K splitting implies
Yeah,
locally symmetric.
essentially. Up to finite cover
Well,
and time change.
essentially.
Essentially.
Implies
Essentially.
essentially, yes. And I think K, I forget exactly how K
So
goes.
it's a quadratic in N or
Well,
something. Is
I think the expectation is that in a lot of dimensions K should be equal to 2.
yeah.
But I think there are problems with getting 2.
Right.
Let's say hopefully. That's about as small as K is going to get in this kind of theorem.
That's stated as a problem in Gromov's.
Anyway, so I think if K is infinity, this theorem is true with whatever the correct interpretation is here. It is a statement that you've got some very, very special geometry. What I want to say though is that the smallest that K is likely to be in a theorem of this nature is 2. When you apply this estimate, the theta that you get is usually less than 1. And the suspicion is that even getting theta better than what this predicts should be rare. Not as rare as theta equals infinity, but pretty rare. And there ought to be theorems of the nature that if you look at an open class of Riemannian manifolds with negative curvature, then a generic subset of them, or maybe even an open dense one, have the splittings have theta not only less than 1, but the theta that this theorem predicts. I think that's what you would hope to be true. You would at least like to exhibit at least some small open set where that's some small set where a theorem like that holds. And so I think paper by Hasselblad, and I think Wilkinson. I think she was also involved in that, and so attempt to find examples of this. And they got into trouble. You can work out, they can show that as long as the sort of Lyapunov exponents do the right things, then this works out the way it should. And then they want to produce examples where the Lyapunov exponents behave in the way they need, and then they have not been able to. So there's a certain lack of examples. This was an attempt rather than a total success. But there's not a lot of reason to think that there's a lot of reason to think that doing better than this theorem predicts is exceptional. And the other thing I should mention is that Anosov was the first one, gave examples where the best theta is less than 1. So he did show that sort of the Hopf approach, well, I don't, maybe it's unfair to call it the Hopf approach, but he did show that the strategy of trying to prove that the foliations of C1 fails, and so you have to use the more advanced technology. Okay, so I think I may say something about the proof of this theorem tomorrow, but I don't think I'll say it now. But what I might try to do is spend the last 10 minutes giving an indication of why we would like these subbundles to be hurled. So, in tomorrow's lecture, it's going to be important to look at stable leaves. Yes, so I want 2 unstable leaves. And then I want a stable leaf that crosses them. So I have those 2 points. And now I want to look at the derivative of f restricted to EU at y. Well, basically I want to look at the derivative of f restricted to EU. And
to take a product along the orbit.
that is where I'm
That's where you want the sum to converge.
Exactly. So I'm just trying to think what it is that I want to compute with this product. I want to, I am going to want to think about this picture, really think about lots of transversals like that. And I'm going to want to talk about how this projection doesn't change volume in the leaves too badly. And in order to be able to do that, if you look at this picture, you can look at it for the rest of your life, and you will learn nothing. What you have to do is move it into the future, when it miraculously changes into a picture like that. And then you have somehow a much better chance of comparing what happens in the 2 leaves. So I just want to think about f to the n x, f to the n y. And the idea is that you are going to, eventually, tomorrow we're going to sort of take some volume in this leaf, move it forward, push it across, and then bring it back. And the idea is that when we push it across here, volume doesn't change very much. And the claim is that that was going to mean that when you pushed it across here, volume didn't change very much. And you think, well, wait a minute. When I went from here to there, my unstable leaf expanded enormously. So there is some ginormous scaling factor. Then I go across and I come back again. There is another enormous factor, which we divide by. If I take a ratio of 2 huge numbers, why should it be have any resemblance to 1? And the proof really, tomorrow's proof really depends on the fact that this number is close to 1. So we want to look at the derivative of f to the n restricted to EU at y, and I want to look at what it does to volume. So maybe I think call that Jacobian of it, and then I want to divide that by the corresponding number of x, and this should be approximately equal to 1. That is really the central miracle in the whole business. So why does this happen? So as we've sort of seen from examples, it certainly does not happen because these foliations have smooth leaves that vary continuously. It happens because the distance from f to the k of x to f to the k of y shrinks exponentially. That is the key to it. Well, there's that plus Hilbert's without good enough continuity of U. So the other calculation that you make, observation that you make, is that this rate, let me call that just Jacobian, say, YE. This thing is a huge product of something like k equals 0 to n minus 1 of the Jacobian of f to the k y comma 1 over divided by Jacobian f to the k. So this just says that df to the n is a composition of n derivatives at n different points. And if you look at how volume expands, you just get a product of the expansions of volume. And then a crucial thing is that if we look at the maps, you go from x to f of x and so on. The maps come in a certain order. And even if you look at the derivatives don't commute with each other. But these Jacobians are just numbers. We're multiplying numbers. Numbers do commute when you multiply. So we can think of this as a product of these quotients. And then we probably want to take a log or a logarithm. So we get a sum. And you determine the sum is going to be a log of the Jacobian minus log of Jacobian at f to the kx, comma 1. And now we know that the derivative, we know f is, I think as long as f is c1 plus something, maybe 1 plus beta, have a new letter, then I will know that df is c beta. And I also know from the kind of things that have been said over here that EU varies and hurled away. So the thing that the map whose Jacobian I'm taking, well, I've got a map that varies in a hurled away. I restrict it to a Hilbert varying subspace. I do Jacobian, then I do logarithm. I end up with a Hilbert continuous function. So if I take the absolute value, I get that this is less than or equal to a sum of absolute values of, well, I guess, absolute values of those things. And each absolute value is less than or equal to some constant times the distance from f to the kx to f to the ky to some power, say alpha. And as long as alpha is positive, life is good. If this distance shrinks exponentially, I have the initial in terms of a convergent power series. And this series, so the worst I can get is the sum of the infinite series, which is finite. So, yeah, approximately equal to 1 really means less than some constant. And the point is that this constant is independent, more or less independent of x and y. The further apart x and y are, the bigger the constant has to be. But that's the only restriction. So this is where the wilderness of the unstable subbundle comes in. And this convergent product is really what makes everything work. So I think let's finish at that point. And I imagine there are just a couple of people in the room who'd be interested in running upstairs and seeing how the cricket is going. So by tomorrow there will be nothing better to think about than Anosov diffeomorphisms, Hilda continuity.
Yeah.
But right now we can do something else.
Yeah.
There is a both these